Hello everybody, the presentation is about direct numerical simulation of a finite cylinder rolling on a horizontal line, horizontal surface, very similar to a rolling wheel on a horizontal ground. And the effect of thickness is addressed. We go through the background and motivation of this work, objectives, numerical method, result, and then conclusion, which is the effect of thickness on aerodynamic forces exerted on the wheels. The background, actually the main, in fact, such a research is mainly funded by automotive industry. So there are lots of research which consider the effect of aerodynamic, study aerodynamic forces on a rolling tire coming from automotive engineering. But actually with wheelhouse in a car or without it. So they consider forces and unsteady fluid structures. But there are some research which consider bicycle tires and in different conditions, like spoked bicycle tires, which here in 2012 a job is done numerically and report negative lift force. But there are other, like cladded tire is studied, or different configuration of bicycle tire is numerically and experimentally studied, which is available in the literature. But Priotzoli in 2012 did a very similar job that is very similar to we've done here, DNS of rolling cylinder in Reynolds, and they considered the effect of Reynolds number in values less than 1000, and they reported that the drag, as expected, decreases as Reynolds number increases, and they reported positive lift as long as they consider just one geometry, and the aspect ratio is very similar to Formula 1 tire. So the missing chain link in this research is the effect of thickness from wheelchair tire or a bicycle tire to a vehicle tire, is the thickness on the effect of thickness on the aerodynamic force, which is addressed in this research. So the objective is the impact of thickness on aerodynamic force. Three thicknesses are considered, from the wheelchair wheel or bicycle wheel to car wheel. The Reynolds number is constant 30,000 based on the diameter of the wheel, which is half a meter. The wheel is rolling so the bottom wall is moving, and the angular velocity is 4 radian per second. From numerical standpoint, the domain is extended 14 d in streamwise direction. The inlet velocity is 1 meter per second constant. The bottom wall is moving. The theta is rotating. The theta is starting from the contact point and rotating counterclockwise. The origin is at the center of the wheel, and the upper wall is a slip condition. 100 million cells roughly is used and clustered around the wheel, and the highest velocity gradient is detected around the stagnation point in the front edge of the wheel, and the delta x plus equals 0.36, which is quite fine, and the calculation can be considered as a fine DNS or a DNS. And a point is, the very important point is that this job should be considered as a low order DNS, because unbounded second order central differencing is used as numerical skill. Instantaneous flow field, here is span-wise vorticity from the thin case to thickest one. As you can see, as the thickness increases, the flow gets more unsteady, and the effect of thickness on the shear layer separating from the apex of the wheel increases as thickness increases. the amount of in fact coherent structures in the wake of the apex of the wheel is higher for thinnest case, but the in fact fluid structures are mainly generated from sides of the wheel in the thickest case. Another important point is that flow in the upstream of the wheel fills the wheel from farther upstream as thickness increases. So this red positive region is larger for the thickest one, in front of the thickest wheel actually. Mean velocity is depicted, is shown in two planes, z equals 0 and y equals 0, and this is streamwise mean velocity, these lines. The velocity deficit is larger close in the wake of apex of the wheel for thinnest one, and this deficit moves downward close to the wall for the thickest one, and the width of the wake increases as the thickness of the wheel increases as expected. Here is CD and CL drag and lift mean value, and interestingly, the thickness, as thickness increases, the CD changes non-monotonically, while CL increases monotonically with thickness. The point is, for the thinnest case, CL is downward, but for other two wheels, it changes its direction and gets upward. So this interesting behavior is a motivation to study parts of forces and then go through drag and viscous parts of each force to study the reason behind this direction switch. Here is average wall shear stress in streamwise direction in the top and wall normal direction in the bottom. And this high wall shear stress region is considered as the attachment line. As thickness increases, flow is less attached, recirculation bubble is larger, so the portion of viscous forces here in a streamwise direction affects mainly the drag force. The portion of viscous forces decreases drastically. For tau y, which affects mainly the lift force, actually the value increases. Just please remember and see this low pressure, low wall shear stress region, which will get disappeared in the thicker case. Actually, for lift viscous force, for first two cases, the direction is negative downward, but for the thicker one is upward. The value increases, but the absolute value decreases. So, in fact, the reason behind this is that the flow is less attached in thicker cases. So the effect of viscous force in lift and drag, either one of them, is less valuable, less important for thicker cases because of the reason that I said. Pressure distribution. Here in the right, this quantitatively we show the pressure distribution on mid-span plane over the wheel, and in the right that's over circumferential face of different wheels. Here is the stagnation point. Ideally should be 1, but here is around 0.8 because of viscous forces and so on. And theta is 0 on contact point and increases in counterclockwise direction. So there is a low pressure region in the immediate downstream of contact point, and there is high pressure region in the immediate upstream of the contact point. Both of them, the negative, the low pressure region, get more negative, and the high pressure region get more positive as thickness increases. But another point is, the high pressure region compensates the lower pressure region in the thicker cases. So about lift force, actually that's, as I said before, that's downward for the thinnest one, and it gets upward for the other two thicknesses. For pressure, this compensation about low pressure and high pressure region doesn't happen, so pressure lift force is still downward for the thinnest one. But this compensation happens for other two cases, and the other two pressure lift force are upward. But the point is, this increase is drastic, and it changes a lot. For drag force, in fact, the change is about 30%, and that's non-monotonic. The ratio of friction to pressure changes drastically, and just only 1% of force for the thickest one coming from viscous force, and 99% of force is due to pressure force, pressure drag force. So in summary or conclusion, I would say that the thickness has tremendous effect on aerodynamic forces, both of them, lift and drag. For consider Reynolds number, the drag force actually changes about 30%, and the contribution of friction force, wall shear stress, viscous force actually decreasing because the flue is less attached, and the recirculation bubble on the side of the wheel is getting larger as thickness increases. The lift force is interesting. That's downward for the thinnest one, but it switches, its direction switches and get upward for two thicker cases. And actually the value of the friction and pressure increases as thickness increases. Thank you very much for your attention.